Welcome to this week's module over error handling and exceptions in C#. And today's topic is one that every single one of you will need to use in every program you write from here forward, because exception handling is how we make sure that our code can handle a problem. Whether the user has given us incorrect information, we connect to a resource we can't access, or the computer just has some kind of error. And you've seen errors happen. Maybe a type conversion has failed. Maybe you tried to divide by 0, or you tried to open a file that didn't really exist. Up until now, when any of these things happened, your program just crashed. A wall of red text, an exception, something that said, hey, an unhandled error occurred. Today is when we're going to take control of that, and we're going to learn how to use the try, catch, finally, and throw keywords that let you anticipate, respond to, and even create your own error conditions on purpose. So by the end of this lecture, you'll be able to write code that fails gracefully instead of catastrophically, and you'll understand exactly when and how to use each one of these tools. So let's start with some definitions. In C#, an exception is an object, and specifically, it's an object derived from the system.exception class. And I tell you this as an important detail because an exception isn't just a flag or an error number, it's a full object with lots of properties and behaviors that we can use. Some programming languages handle errors differently. They use return codes, or a function runs, and instead of throwing anything, it just returns a number. And you're responsible for remembering to check that number every single time so that you actually know what the problem is. The problem with return values is they often serve multiple purposes, so it's very easy to forget to check or to misinterpret what a particular code means. So let's take a look at some of the differences. Error codes is just a flag or a number, and they can be easy to ignore, or they can have multiple purposes. There's no built-in detail about what actually went wrong, and the caller of that method or that function has to remember to check every time for that particular error code. With .NET, we get a rich object that carries full context about the failure. It's designed only for failure reporting, and it carries a message, a full stack trace showing exactly where things went wrong, and critically, it can't be kind of silently ignored. If you don't handle it, you've seen what happens. The program loudly tells you that an unhandled exception has occurred. So when something goes wrong with our C# code, we say the runtime throws an exception. And that word throws is going to come up constantly in this lecture, so get comfortable with it. It means that an exception object has been created and is now being sent up through your code, looking to see if you've prepared to handle it. So how do exceptions travel? Because I just said that it travels through your code. So when an exception is thrown, maybe deep inside some method, how does it actually get handled? The answer involves what we call the call stack. So if we think about how our program runs, main maybe calls process order. Process order calls calculate total. Calculate total calls divide. We have steps that we've gone through to get to the different parts of our application that we want to run. Each of these is a method call stacked on top of the previous one. That's how the compiler knows where to go back to when the method resolves. And if you've used breakpoints to debug in your problems before, in your code, then you've seen this happen in real time. As a method resolves and we've stepped through it, the compiler knows exactly where to go back to as the previous point of execution, maybe in another class or another method, or back to the main. This is what we call the call stack. So imagine that divide, at the very bottom of the stack, throws an exception. Maybe someone tried to divide by 0. The thread, that's the open memory gate that's currently actively working this call stack, immediately suspends. The runtime asks, does divide have a try catch around this code? Is it prepared to handle an exception? If the answer is no, the exception is going to start to climb up the call stack to whoever called divide. So it's going to come into calculate total and look, does calculate total have a try catch that's prepared to handle my exception? In this example, yes. We can see the green box with the check mark. So because calculate total has a matching catch block, the exception is going to be handled right here. It never needs to climb any further. Process order and main never even know anything went wrong. But, and this is the critical part, if calculate total wasn't prepared to handle the exception would keep climbing. It would go to process order and then to main, and then if none of those methods catch it, the program terminates and you get that big error message that says an unhandled exception has occurred. And this right here is actually the safe, intentional behavior of .NET. Crashing is better than trying to continue to run in a corrupted or unknown state. The job as a developer is to add in these try-catch blocks at the right level in the stack, not too low where you don't have enough context or information to fix the problem, and not so high that you're catching things and you don't understand where they came from. So I'm talking about this try-catch block, and maybe you're like, what are you talking about? So a try-catch block is our exception handling code. They are two keywords that we use together constantly. We put any code that might fail inside of a try block. If that code throws an exception, execution will immediately jump out of the try block and look for a matching catch block, where we write the code that responds to the problem. So if we look at the example, we have a numerator of 10 and a denominator of 0. Dividing by 0 with integers in C# throws a divide by 0 exception. And this is a good example because it's something you may have already run into accidentally. The division happens inside of the try block. Below it, we have a catch specifically typed. We can see catching a divide by 0 exception with a variable named EX representing the caught exception object that gets created. Inside of that catch block, we can use EX's .message property, which gives us a human-readable description of what went wrong, and we write that out to the console. So if we trace through exactly what happens, step 1, the code enters the try block and starts running normally, so nothing unusual yet. Step 2, the division by 0 actually throws the divide by 0 exception. Step 3, execution doesn't continue line by line inside of the try block anymore. It immediately jumps to the matching catch block, and the catch block runs the exception's message property, which gets printed to the console, and the program keeps running afterwards. We didn't crash, we handled it. And so this is the pattern you want to use again and again. Isolate risky code in try, respond to failure with catch. So let's look at another example, because real code rarely has just one possible failure. We might have several different things that could go wrong inside of the same try block. So you might want to respond to each one of them differently, and C# lets you stack multiple catch blocks, each one targeting a different exception type. So in this example, we have one try block followed by two separate catch blocks, one which we can see is typed to the argument null exception, and one for argument out of range exception. When an exception is thrown inside of the try block, C# checks each catch block in order from top to bottom and runs the code in the first one that matches the exception's type. So this brings us to kind of a rule that's important and can trip up a lot of new developers in C#. The order matters. So catch blocks are evaluated top to bottom. So if we are looking for more specific exception types, we need to put those first before the more general ones. So if we catch in the base exception class first, it would match literally everything, because remember, base classes are going to be the base for all of these different types of exceptions. So if you just use base class exception, then none of these more specific catch blocks below would ever run, because C# is going to stop at the first match. So our warning box reinforces a principle from our earlier reading. We catch only what we understand and can actually handle, or maybe anything that you specifically need to log. If an exception type shows up that you didn't anticipate and you don't know how to fix, the right move is often to let it propagate up rather than catch it and potentially hiding a real bug. Now let's add a third piece to the puzzle, finally. The finally block contains code that runs no matter what happens in the try block, whether an exception was thrown or not, and whether it was caught or not. If you include finally, it always executes, but it is optional. This makes finally perfect for things like cleanup work. It can close files, release network connections, dispose of any resources that absolutely must be cleaned up, regardless of how the operation turned out. So in the example here, we're trying to open a file using StreamReader. If the file doesn't exist, opening it is going to throw a file not found exception. We can catch and print a message for this. But look at the finally block at the bottom. It checks to see if reader is not null, and if so, calls reader.close. Since finally runs whether the file opens successfully or not, this will guarantee we never have to leave a file handle open, which could just be chewing up memory in the background. So on the right, you can see we map out 3 possible paths through this code. The first scenario, everything goes great. No exception is thrown at all. The flow is simply try and then finally. In the second scenario, an exception is thrown and caught. The flow is try, then catch, then finally. In the third scenario, and this is the one that sometimes people forget, an exception is thrown but not caught by any of our catch blocks, because our catch block is only looking for a file not found exception. The flow is still try and then finally runs, and only after that does the exception continue propagating up the call stack to potentially and hopefully be handled elsewhere. The third scenario, that's the kind of the real power of finally. Even when you don't catch something, your cleanup code is still going to run before the exception keeps traveling. So we've talked about catching exceptions that the .NET runtime throws automatically, things like divide by 0, file not found, and so on. But you can also throw your own exceptions intentionally using the throw keyword. And so this is how you signal that something in your code's logic has gone wrong. So take a look at our example here with setAge. It takes an integer age, but before it does anything else, it checks. If age is less than 0, that has to be invalid. So instead of silently storing that bad value, we throw a new argument out of range exception. With a clear custom message here, age cannot be negative. Only if that check passes do we actually go ahead and set this.age. The callout box below the code reinforces hopefully what's happening. Calling setAge with -5 doesn't quietly store -5 into the age field because that wouldn't be appropriate. It immediately raises an exception with a message that tells you what went wrong and why. So that exception is going to start traveling up the call stack looking for any catch block that would be able to handle it. And there are reasons for why we reach for throw in our own code. So we want to signal an error condition that's instant, it's detected. All of that .NET framework things, the compiler things that we use inside of our ecosystem to help us, by using throw and calling an exception, it's going to allow that system to work as designed. We don't want to let bad data quietly continue downstream where it might cause a much more confusing failure later. Throwing also lets you propagate the problem to higher level code that's in a better position to decide how to handle it. Maybe that's what the caller wants to have happen, so the user can retry. Or maybe they want to show a friendly error message to the user. Your low-level method doesn't need to make that call. And so this validation technique, where we're checking our method's inputs and essentially failing fast with a message that makes debugging much easier than a generic crash, is what we want. That's what we're going for. So we've covered all 4 keywords: try, catch, finally, and throw. So let's wrap up the technical content with some best practices that separate exception handling that helps you from exception handling that just creates new problems. So first, exceptional situations only. Exceptions exist for genuine error conditions, not as a substitute for normal control flow like if statements or loops. If you find yourself using try-catch to handle something that's actually a routine or expected outcome, that's a sign that you're kind of misusing exceptions and should restructure your logic instead. Second, catch only what we understand. Only catch exceptions you can actually handle meaningfully or that you specifically need to log, and we should catch them where they need to be handled. If an exception type appears that you don't recognize or don't know how to respond to, letting it propagate up the call stack rather than catching it and potentially hiding a real bug under a vague error message is the better way to handle that. Third, write meaningful messages. When you throw your own exceptions, take the extra 5 seconds to write a clear and specific message. Something like age cannot be negative tells you immediately what happened and what the problem is. A generic message like invalid input forces you to dig through the code, evaluate, and debug to figure out what actually went wrong. Future you, debugging at midnight, will thank present you. Fourth, using the using statement for anything that implements iDisposable. Now, I know this might go a little over your head, but you've seen examples of this when using maybe file streams, network resources, or database connections where we're using a using statement inside of the code to call something like a stream writer. The using statement automatically calls the dispose for you when the block ends, which means you get guaranteed cleanup without manually writing a finally block every single time. It is essentially a finally block built right into the language for this exact purpose. And so if you are in that situation where you are thinking about that structure or you're not sure how it works, or if you need a finally block, hopefully you can remember that I told you it comes built in. So let's bring it all together. Exceptions are in C# are rich objects derived from system.exception. They're purpose-built for failure reporting, not multi-purpose return codes that are easy to ignore. We can catch specific types of exceptions, and you can go research system.exception and look at all of the different ones out there that are available. Or if you're not sure what you are going to catch, but you want to make sure to catch it, you can catch generic exception. When an exception is thrown, it climbs up the call stack looking for a matching try-catch. If it finds one, it's handled there. If it never finds one, the program terminates with an unhandled exception. Try should enclose code that might fail. Catch handles specific exception types, and when you have multiple catch blocks, make sure to order them top to bottom from most specific to most general. If you want your very last exception block to just catch exception, you can do that, and it will catch any of the specific ones if those occur, or any exception, because exception being system.exception is the most general. Finally always runs, but it's optional. So if there's an exception, finally runs. If there's not, finally runs, but you do not have to put a finally block if it doesn't make sense. So this makes it the right place for cleanup code like closing files or connections, but if you're just wanting to handle the exception and then move on, You don't need a finally block. Throw, the keyword, lets you explicitly raise your own exceptions the moment you detect an invalid condition in your code with a clear message explaining what went wrong. You can throw any system.exception derived exception class, or .NET lets you write your own custom exceptions that are derived from system.exception, and you can throw those as well. And then again, best practice, only catch what you understand and can meaningfully handle. Let everything else propagate up rather than just swallowing it silently. So I hope you've learned quite a bit about exceptions. I am going to raise the bar a little bit on your assignments and start to ask for and look for the use of try-catch blocks throughout your code so that you can start to get into the habit of writing these and using them in every place that it's appropriate. So good luck, and remember, the goal isn't to prevent every possible error. It's to handle the ones you can and fail clearly and safely where you can't. Reach out with any questions. I'm here to help.